two tough questions. So this is actually going to be on quantum mechanics and space-time, so I've checked off those boxes. So let me start by reminding everyone well, let me start by saying this is work with Mike Friedman that appeared in April. And at the end, if there's time, I'll talk about time, so the whole talk won't have time in it until the end. And that work is ongoing with Veronica Hubany. So let me start by reminding us of things we know. So for a long time now, since around the time I was born, we've known that in semi-classical gravity, there's some kind of a universal relation between entropies and surface areas. So there's something very special about codimension 2 in gravity, and codimension, the units of area are the units of Newton's constant, and somehow, and so you can make a dimensionless number by taking a surface area in Planck units. That's a very natural thing to do, and it turns out that that number that you get somehow is an entropy. So the original example, of course, is a black hole. So we have, Bekenstein-Hawking. Is it okay if I write down here? Is this okay?
That's
it. All right. So that says that when you have a horizon, that's given by the area of the horizon, and we have this covariant entropy bound where you get an inequality. The entropy of something is so this one is more general. The area of a more general surface, and then of course we have in holographic theories we have the famous Ryu-Takayanagi formula, which says that given some region in the holographic theory, the entropy, the entanglement entropy of that is given by the area of the minimal surface in the bulk. So this is our bulk minimal surface, which is, let me write it like this, homologous, meaning homologous means that there's some region in the bulk that interpolates between A and M of A. Okay, so these are things that we've heard before, and of course the big question is why? And I think that when this is what we had, you see, it was originally a statement about horizons. The area of a horizon is given by, is telling you the entropy. So the horizon of the black hole tells you the entropy of the black hole. So then, since a horizon is kind of a special place in the space-time, in some sense, you could say, well, there's something very special about black holes or other types of horizons, and somehow the state is encoded on the horizon. Maybe, you have little zeros and ones. Each one occupies a quarter of a Planck area. Each one occupies 4 Planck areas, and that's kind of why, to describe the state of the black hole, you need a number of bits which is equal to the area of the horizon in Planck units. Okay, and you can see in sort of popularizations of that discuss Bekenstein-Hawking entropy, you'll see pictures like this. Okay, and it's sort of the obvious conclusion, and then you scratch your head and wonder, what does this mean, and so on. And so the thing that Ryu-Takayanagi does for us is, because it's such a vast generalization of Bekenstein-Hawking, it really allows us to probe that picture. and many other questions about entropy and gravity. And so what I want to do is to use the fact that it's such a large generalization, in other words, the fact that whereas this is restricted to the horizon, now I have a new variable that the entropy is a function of, so I can vary this variable and thereby vary the surface and sort of test this idea. So in particular, I mean, this is admittedly a little bit of a straw man, but I want to kind of say some things about why I've been, since the beginning of Ryu-Takayanagi, a little uncomfortable with it. So the straw man is the idea that the answer to this question is that the state of A is encoded in the bulk in some way that's localized along the minimal surface at a rate of 1 bit per 4 Planck areas. So that you should think of the bits that's living on the minimal surface, which would account for this formula, okay? And so what I want to do is sort of give some reasons why that naive picture maybe doesn't quite make sense in order to motivate a new picture, which I think makes a little more sense, and in sort of giving you a picture you can have in your head of quote-unquote where the bits live, okay? And to do that, what I'm going to do is I'm basically going to rewrite this formula just in a new way, okay? Okay, but first, in order to make that reformulation seem more interesting, let me say what I don't like about this standard formulation. So I'm going to give 3 objections to the idea that the bits are living on the minimal surface. So let me first write.
The bits that are entangled.
Yeah, the bits necessary to describe the state, the microstate of A. So A is actually in a mixed state due to entanglement, and
but suppose A was just unentangled with the other guy, with A complement. Then it could have a very complicated microstate, but it would have no area.
no, within the macrostate rho sub A. So then rho sub A would be pure, and then 0 bits would be required to specify the microstate of A. I mean, if you knew rho sub A, right?
I see.
Yeah, because that's the entropy.
I see.
I mean, in other words, okay, it's because of the mixed nature you're saying of rho sub A
Yeah.
that you need some number of bits.
Right, right. Yeah, the entropy is the number of bits required to specify a state, a pure state within the given mixed state. Okay, so 3 objections. Well, the first is that the minimal surface, if you change A in a continuous fashion, the minimal surface can jump from one place to another, which is odd if the...
Just to understand the rough picture.
Mm-hmm.
So is this straw man idea that the bulk inside A would encode the whole of rho sub A, and then some bits on the boundary would tell you which state in that?
Well, there is an idea that that the inside is the holographic representation of rho sub A, in the same sense that a black hole space-time is a representation of a thermal state,
Right.
and then
the actual state within that row is somehow encoded on the other.
yeah,
Is that
you could think of that.
Okay.
Yeah. Right. I mean, what we have here is, of course, is a classical space-time. We're working in the n goes to infinity limit, and then somehow, so somehow rho sub a is a classical object, and is defined in this same n to infinity limit, and then somehow, specifying the microstate is like a very quantum question within that, whose answer would, live on the manifestor. Okay, so the first objection is that under continuous deformations of A, M of A can jump.
Sorry, man, sorry to interrupt, but just to understand this picture again for black holes, I just want to understand this is a standard picture for black holes. So suppose I take the exterior of a black hole geometry, let's say within any case.
Mm-hmm.
Okay? And it's clear that for many purposes the exterior of that geometry captures the thermal density matrix.
Mm-hmm.
Now, but is there some belief or some standard picture that there's some additional information living on the horizon that captures, that specifies which state within the sensitive matrix?
I've never heard that made extremely sharp, but I think there is. Yeah, I mean,
But is there any serious relation that this is the case? Whether sharp or not?
I mean, to the extent that one might think that the interior of the black hole is entangled with the exterior and thereby giving rise to the density matrix from the outside, then if you believe that the interior is actually captured by 1 bit per, whatever 4 Planck areas, then you may say, okay, it's
well, I mean, for example,
degrees of freedom that do it, right?
Yeah, I mean, so if you think that the Bekenstein-Hawking formula is related to the fact that entanglement entries in field theories have an area law divergence, and of course there's the issue of the coefficient and so on, and probably this should not be taken too literally, but of course that area law divergence is local. The reason it's an area law is because it's local along the entangling surface. Okay, so that in that context it seems like a very reasonable thing. I mean, I've heard people, ask the question, where do the bits live? For example, Juan in his strings talk at the very end, which was good for me because it was right before my talk, asked the question, he ended his talk by asking the question, where do the bits live? And his question was kind of, in some sense, how far from the horizon do they live? Are they in the stretch, should we think about the stretched horizon and all this whole business? But in terms of something more quantitative than that.
N equals 4 Young's, I would think of the exterior of black hole, the geometry, as some solution of the large N master field of Young's theory,
Mm-hmm.
whereas the bits are the gluons. And I'm trying to see whether I can somehow...
But you agree that the existence of a horizon is related to the fact that we're in a mixed state.
Yeah.
Right? So it sort of stands to reason that...
It could be... Okay, I mean, it could be that this is a diagnostic that there are mixed states, but it's not the description in which the mixed states live there. I mean,
Absolutely.
Yeah.
But all I'm saying, I completely agree with
Yeah.
you. I completely agree. That's why I called it a straw man. But you have to agree that the first thought that jumps to mind, if you see a formula like this, is what I said before.
Absolutely.
Okay. Okay. So, and if you follow that line of thought and you use the fact that we can vary A, then you sort of paint yourself into a corner. Okay. And I'm not saying it's the only way you can paint yourself into a corner. It's just one way. Okay. So an example of this is if our A has 2 parts. Then we can go from a situation in which M of A. So as we, for example, change the separation between the two subregions of A, when they're at large separations, you'll find that the minimal surface is the union of the two respective minimal surfaces. And when they're at large separations, when they're at small separations, you'll find that it's not. So, you'll find a minimal surface which looks like you'll find a minimal surface for the union which actually joins the two. And at some point, it jumps from one to the other. It's a sharp first-order type phase transition, quote-unquote phase transition. So the place where the bits are, so if you happen to sit on the phase transition point, then where are the bits? Are they in one place or the other place? Okay.
This is only a large C thing, right? If you go to higher orders in consider the higher direction, this transition is not sharp anymore. It becomes sort of smooth, right?
Yeah, but of course this formula only applies in the large C limit. Of course, if you move away from C equals infinity or n equals infinity, then of course your background is fluctuating, and the effect you're talking about is actually a non-perturbative effect in 1 over C. Then of course, we're not doing classical holography anymore, right?
Even if we consider just the 1 over C correction?
The 1 over C corrections, perturbative corrections can never smooth out a phase transition, right? So that particular effect is due to non-perturbative corrections. Actually, I mean, as a side note, no one has understood the nature of those corrections. I think that's actually a very important open problem in studying holographic entanglement issues.
The 1 over C correction?
The non-perturbative corrections which smooth out this phase transition or other subspace.
Is there in principle description of the Ryu-Takayanagi formula at finite?
No. The first perturbative correction is reasonably well understood.
Yeah.
That's as much as far as we can go. Yeah.
That's this.
Right, this Malthus
loop.
Faulkner, Lukowitz, Maldacena.
and the earlier, the Maldacena, Lukowitz, whatever, the derivation,
Yeah.
quote-unquote derivation of Ryu-Takayanagi was something very classical.
Yeah, that was purely classical. Yeah.
And it didn't seem easy to extend. It's just some statement about classical differential.
Well, yeah. I mean, this goes into. I mean, you could ask the question, which I think is maybe a topic for a different seminar. Given that we have this derivation, why can't you just crank it and find out what the non-perturbative corrections are? And if you do, you fall right on your face. I mean, it's quite interesting actually that you failed very, very badly, which actually shows that the derivation is a little bit fake, because it's not that you find the original answer you thought you had plus a correction. You find the original answer was wrong when you include what you thought were small corrections, which means you don't really know what you were doing. So that's actually
Harlow has a reformulation where it's all exact, and it's not expressed really in terms of areas, but it's
no. What he has is something that gets the FLM corrections.
Well, he claims
But-
it's exact.
The area part he just puts in by hand.
I see.
Yeah. No, he has. There's no derivation of that part.
I see.
Yeah.
Well, you should tell later, but I thought at root you're doing the replica trick in the bulk, and then
Yeah.
in the classical limit, okay, it gives you the area, but
Yeah.
more generally it's what it is, and that would be the more general.
Well, but we don't understand how to do, non-perturbative quantum gravity well enough to apply the replica trick, accurately enough to obtain these corrections. As Shiraz is saying, it's all classical,
Yeah, and in particular, they were solving a differential equation. They admitted a solution with a singularity, and then from the point of view of differential equations, you could argue that it was okay, maybe. But to make sense of quantum corrections around that singularity would be really hard.
We should talk about it.
Yeah.
Yeah.
Yeah, no.
Disturbed because I thought it was better than what you made it to be. So, okay. We should close by 1:15 so we get 45 minutes.
Okay. So related to this, closely related to this objection, is the following: that if you want to compute certain quantities from, so that there are certain quantities which you can compute from entanglement entropies, as linear combinations of entanglement entropies, that capture essential aspects of the correlations and so on in a state. And you can, so examples are the conditional entropy. I'll talk a little more about these in a second. Let me just define them. And the mutual information. So, if you want to compute these using Ryu-Takayanagi, it's no problem because we know how to compute each of these terms. And that's great, but if you ask yourself, why am I subtracting the area of one surface from the area of another surface that passes through an entirely different part of the space-time, then you get confused. So for example, in a case like this, if you say, okay, I would like to compute the mutual information, well, that's fine. And let's say we're in the regime where the minimal surface for A1, A2 is this blue one, then you would take the area of the orange thing plus this orange thing minus this, and you would get an answer. Now, let's remind ourselves why we're interested in these kinds of linear combinations. So, and let me just do start with just the classical case. So let me just talk about the information theoretic meaning of these quantities. So the classical case, this is going to be very rough, but essentially when you have your state of AB, you can encode that in some string of bits whose length is the entropy of AB. Meanwhile, the state of A, entropy of A, B, entropy of B, and you can encode the whole thing in something like this, where I have some number of boxes. Each box has a bit in it, these boxes, so this is supposed to represent the state of A, this row of boxes represents the state of B, and it's such that, so a given state would be like whatever, but the box on this row would equal the box on this row. Okay, so that the total number counted this way is S of AB. So this is how many bits you need to specify the state of AB. This is how many bits you need to specify the state of A. This is the number you need to specify the state of B. And they have some number which correlate. And then, of course, if you just do the math, you see that this number here, the overhang here is the conditional entropy. And so that's the number of bits of AB that are purely in A. And the mutual information is the number in the overlap, which is the number of bits that are shared or redundant. Okay, so that's how classical states are organized. Now, of course, in the quantum case, it's much more complicated, and in fact, I can't draw a simple picture. But a special case would be where you have entangled pairs of qubits, and then so if you have some number of entangled pairs, so an entangled pair.
So just understand, in your classical picture, the entropy of A is just the entropy is 2 to the power number of bits, log of 2 to the power.
Yeah. In my talk, 1 to S of B, so it contributes 2 to this and minus 1. So here are 2 bits. 2 minus 1 to both of the conditional entropies. Okay, so now let's go back to this picture, and I don't see, if the bits are living here, of S of AB are living here, and the bits of S of A, call this A and B, and the bits of S of A are living here, and the bits of B are living here, they're in totally different parts of the space-time, which may not even know each other. I mean, yet somehow, magically, the differences here are telling us how many bits are purely within A, how many bits are purely within B, and so on, how many bits are correlated or shared between them, and so on. So what I'm saying, I mean, there's nothing wrong with this formula, but conceptually, it's not matching up with its information theoretic meaning. What I'm saying is it seems to be keeping some secrets from us. Okay? And my third objection is just along the same lines. In fact, maybe I'll just put it here.
So roughly this objection is similar to the fact that, the surface which seems to encode for AB is so different.
Yeah, it's somewhere else. It's somewhere else. Yeah. So there's this proof that that Ryu-Takayanagi obeys strong subadditivity, and it's essentially just again taking differences of surface areas that are in different places and kind of arguing that some difference has to be positive. The meaning of strong subadditivity, well, there are many ways to say it, but one sort of way to say it is that it tells you that the mutual information is monotone, which is consistent with it being a measure of correlation. So you have this inequality, okay? And it's never been clear to me what the proof that Ryu-Takayanagi obeys strong subadditivity is very simple, but I never understood what that proof has to do with the meaning of the, it just seems like some miracle or an accident or something that this formula obeys this property. There's nothing complicated about the property itself. So I've always been quite confused about this whole business.
Sorry, say the last thing again. So you're saying this inequality is, it does come out, of course, from the bulk geometry.
Right.
And what was
Right. So yeah. Okay, so we have this amazing formula. We want to use it not just to calculate entropies in all kinds of different backgrounds and write lots of papers where you've calculated it here and calculated it there. We want to use it to learn something about quantum gravity. Okay, it should be telling us something, or at least about holography. And so that part I haven't found it very satisfactory. Okay, so what I want to do...
Sorry, when you say proof, you mean the proof on the gravity side?
On the gravity side, the holographic proof. The holographic proof. Okay. So that leads me to so that was essentially the motivation. So what I'm going to do is I'm going to just rewrite this formula. I'm not changing, it's the same formula, I'm not making any new proposal or anything like that, it's exactly the same formula. But I think the new way of writing it is conceptually helpful. That's what I'm going to argue. and you know, and in some sense, I think the new way of writing it leads to its own questions, but maybe that's helpful. It's not gonna like solve everything. Okay. So I'm going to use a theorem from differential geometry. Actually, the theorem is originally from network theory, but it has a version which is in differential geometry, which is the one that I'm going to present. Okay, so we have some Riemannian manifold. Again, I'm not doing time in this talk. So M is some so this is just I'm just going to give you a geometry theorem. Okay, we'll do the physics in a second. Okay, so I define a flow. A flow, by definition, is a vector field that obeys two conditions. It's divergenceless, and it has norm less than or equal to 1 everywhere. Okay? And the theorem is like this. So let me,
I see, and it can vanish.
it can vanish. Yeah. The theorem says that for a subset of the boundary of M, the minimal area surface homologous to A is equal to the maximum over all flows of the flux through A. So this is unit normal. Okay, we need a picture. So here's the picture. So, you know, you basically have some pipe or whatever, some topology. I don't care what the topology is. And let's say for the first picture, let's say A is this whole boundary. Okay, and on the one hand, you want to find the minimal area surface, which is homologous to A, which in this cartoon might be somewhere in here. Maybe this is your minimal area surface. And on the other hand, you want to put as much, basically, water through this pipe, you know, as you can. Okay. Well, okay, that's a bit of a mixed metaphor because maybe I shouldn't have said that. Let's consider this to be a cartoon of a two-dimensional surface. So forget the pipe business. You want to put as much flux of a vector field, a divergenceless vector field, as you can into the manifold coming out of A. Okay? Now, the vector field is divergenceless, and so we can represent it by some flow lines, which would come out of A, and they go somewhere. Okay? And you're trying to maximize the number of flow lines subject to this condition, the divergenceless condition, and the fact that their norm is less than, the norm of V is less than or equal to 1 everywhere, which means basically the norm of V is the density, the transverse density of flow lines. Okay? So the transverse density of flow lines is not allowed to be arbitrarily large, and as a result, when you, let's say you start putting in flow lines, you keep adding them, and at some point you'll get stuck. Where will you get stuck? You'll get stuck where there's a bottleneck, okay? And where is the bottleneck? The bottleneck is at the minimal surface, homologous to A.
So these words already prove that the maximum flow is less than equal to.
These words, yes. So the fact that this thing is less, so the fact that this is greater than or equal to this, it follows from these two directly. And the non-trivial thing, which one has to prove,
You can always
is that it's saturated. Basically, that this is the only obstruction to adding more flow lines. Okay.
Sorry, so the left-hand side is so you take an area A, as you said, part of the boundary, and then what is area of M? Oh, and then you take something homologous to A and take the minimum. Just define the left-hand side.
Yeah, so this means surface is homologous to A.
Mm-hmm.
So we look at the space of all surfaces homologous to A,
Mm-hmm.
and we minimize the area.
The area, okay, so that minimum area equals, and on the right-hand side you have n dot v integrated over the boundary A.
Yeah, over the
Maximum
part of the boundary A.
Flux coming out of it.
Yeah, the flux coming out of A. The flux coming out of A.
Okay, so
Okay.
you say the maximum flux coming out of A is the, okay, got you.
Yeah, and from now on, I'm going to stop. I'm just going to write this, which means the flux of V coming out of A. Okay, I'm not going to write. I mean,
N dot here.
and this is what we could also have called the area of M of A. In fact, let me write. So M of A, by definition, is the minimizer, and so this thing, by definition, is the area M of A.
Does this complete the definition of V?
How what?
How you determine V? How you completely determine V or no?
So I'll talk about what V is in a second.
The V is not unique in fact.
Yes, so I'm gonna.
But the area is unique, right?
The area is unique. Well, yes. So
We
the only claim here is that the value of the left-hand side is equal to the value of the right-hand side. Okay. I'm going to talk about V in a second. Okay.
But it's not about, okay, from this picture, you can have the flow lines coming from many
I
parts
think
of
we
it.
lost Bangalore.
Here it comes.
Oh, okay.
There are many flows that have hit the same bottom tank.
Right. So since you asked the question, why don't I just go ahead and say so on the bottleneck.
And for any different V which satisfies the above two conditions, there will be many different V's which satisfy this condition, right?
Of course, there are many different V's that
And all of them
satisfy.
will give the same area.
No, the V's that you mean there are many different maximizing V's? Or V's that satisfy these conditions?
There are many different V's that satisfy this.
Yes, there are many different V's that satisfy, yeah.
And I have to choose a particular V which maximizes this.
Yeah.
Is it?
But that the choice is not
Yeah.
unique. There are many different V's that also maximize.
But then how can I get the same area?
Because they all maximize.
They all maximize, they all have the same value. If they have different values, you would just choose the one with the maximum. Yeah.
In a picture, could A have been half that circle?
Yes, I'm going to draw that in a second. Yeah. So A doesn't need to be closed. In this first go around, I made it closed because it's maybe for pedagogical purposes. But good. So as Shiraz rightly points out, there are many different V's that maximize the flux. The thing is that on the minimizer, the only way this quantity could ever equal the area of the minimal surface, given this condition, is if on the minimal surface, V is equal to the unit normal. But away from the minimal surface, you have tons of freedom. These are very underdetermining conditions. Okay? While M of A is generically unique, except for these kind of phase transition situations, the maximizing V is far from unique. Nonetheless, I will give it a name. And if anybody has an idea for a better notation, let me know. So I'm just going to use V of A to denote any maximizing flow.
parameters in that?
Yeah, I mean, so essentially, you can make V, there's some, basically, let's see, what should I say? So the space of flows is some function space, but it's a bounded function space because of this. And the condition that you maximize cuts you down, of course, within that function space because of this condition. But essentially the dimensionality, if you want, of that function space is as big as it could be, except for this condition. In other words, locally you can make V anything you want, as long as you're away from the minimizer. You know,
Isn't it codimension 1? Isn't there just one condition on that?
no, this is pointwise on.
Oh, sorry.
This minimizer.
Yeah.
So, you know, a very nice way to think about it is in terms of the flow lines.
Sorry, I missed something. So VA has the property that on the minimizer it is always equal to the unit.
On the minimal surface.
I mean, that seems very reasonable. I'm just wondering, would it be that you can't achieve that? Or
Right, so the theorem is that you can achieve that. The theorem is that there's no other obstruction, essentially. There's no other obstruction to solving this equation. Yeah. Yeah, and that part is, it's not actually that hard to prove, but,
Sorry, if the flow is a function of d variables, then it's codimension a function of d minus 1. Is this right? Whatever that's very formulation. Because
it's codimension a function, yeah, in a sense.
Yes.
Yeah, that's right.
Huh? What?
Can you explain that?
Well, the flow is a function of d variables that describes the flow, and you've got a condition on a d minus 1 dimensional surface, a functional condition on d minus 1 surface. So
That's the codimension.
yeah,
Um,
right. Therefore, function.
So you can think of the flow as a set of flow lines, which I'll call threads, that can't begin or end anywhere in the bulk. They begin or end only on the boundaries. And their transverse density, which is equal to V, is less than or equal to 1. And so then what I want to say is that the flow lines, again, are maximally packed together on the minimal surface, but they're very floppy away from it. Okay? Okay, so now we are ready to reformulate Ryu-Takayanagi. This part, hopefully, it's not going to be very surprising what I'm about to say. So, and here, by the way, now I'm also setting origin usually equal to 1. It's also, if you want, the maximum number in words of threads coming out of A. Okay, so in other words, you have these threads, and they have a rule. Well, they have two rules. One rule is they don't begin and end in the bulk. The second rule is, for some reason, they are not allowed to be packed together more than a transverse density of 1 per 4 Planck areas. So each thread, if you want, has a thickness. It's like a hardcore repulsion with a thickness of 4 Planck areas. Okay? And then, subject to those rules, if you want to know the entropy of A, you just find out how many threads you can put in the bulk leaving A. And you're interested in the net number leaving A. Okay? And that is the entropy. Okay? So that's the picture. Let me actually draw it for the case when A is not like a whole boundary here. And we don't care where they go. They can end in various places. They can end somewhere else on the boundary. So on the complement of A, they can end on a horizon, if you happen to have a horizon in the bulk. They can even end on A itself, so you are allowed to have a thread which begins and ends on A, but such a thread, of course, doesn't count toward S of A. So this is really the maximum net number. So these are oriented.
So those threads don't contribute to the flux.
Right, they don't contribute to the flux, and so they don't count computing nature. Okay?
You could have some threads coming back
Exactly, to A.
to A from somewhere else.
Oh, that's true, yeah. But in your maximizer, you'll never have that. Okay, that's true. So, in this picture, what is the role of the minimal surface? The minimal surface is just a convenient way to calculate the maximum number of threads. So basically, the minimal surface is wherever the bottleneck happens to be, which is stopping you from adding more threads. And it's convenient because on the bottleneck, the threads are maximally densely packed, and so you can calculate the number of threads by just counting the area. That's the only thing that's special about that place. It's the place where the threads happen to be maximally packed together. Okay? So, I want to say that, so for the rest of the talk, I'm going to basically talk about the conceptual implications of this picture. But I should say that it's not hard to imagine that actually this formula might be useful in practice calculationally for computing entanglement entropy. So actually, in certain fields of computational geometry, like certain image processing problems, they use max flow min cut as a good algorithm for like edge detection and things like that. The basic reason is that the right-hand side here is what's called a convex program. So it's a convex optimization problem. You have a convex space on which you're maximizing some concave function. And that type of problem, there are extremely fast algorithms for solving them. Versus the usual finding a minimal surface, you're in sort of a nonlinear space and you're trying to minimize a function which has all kinds of local minima and stuff like that. So it's kind of an annoying problem to try to solve computationally. Okay, so I just want to throw that out there.
Sorry?
But I think it does depend upon some global features of the manifold, the bulk manifold, right? And you have to know something about it.
You have to know everything about it
Yes.
in order to figure out what the maximum number of threads you can put is. Yeah. It's still just as non-local. I have not made the problem of computing entanglement entropys in any way local. It's exactly as non-local as it was before.
So just to continue that, suppose you find a flow that exits. Actually, you don't even know where the bottleneck is.
Exactly. Yeah. Yeah, you have to solve those constraints everywhere in the whole manifold to be sure that you've got the right thing.
So Matt, if there's a black hole, then of course the flow lines can end on the black hole horizon.
Yes.
But let's say you just have a hole cut out manifold. Then what's the rule?
Right, good. So if you have like a wall or something, like you have a confining theory and there's a wall, the threads are not allowed to end on that. If they hit it, they've got to bounce back. And the basic reason is, well, of course, the basic reason is that's what you need to do to get the right answer. But conceptually, the reason is that boundaries of the bulk like that don't carry entropy. Horizons carry entropy, but boundaries like that don't carry entropy. I mean, the other thing, you don't actually, if you're talking about smooth walls, you don't actually have to impose that as a separate rule.
That's what I was going to say. I mean,
Yeah.
oftentimes in confined space, it's smooth, and it
Yeah.
just automatically.
But if you had like an orientable fixed plane or something, you would have to impose that as a rule. But it's very natural, I think. Yeah, that's a good point. And I want to repeat the fact that, of course, the threads are very floppy away from the minimal surface, and so you have this freedom to move them around, and in particular, you have the freedom to move around where they connect to A, and you have the freedom to add, because there's so much space up near the boundary, it's very empty in there, and so you have the freedom to add tons of extra threads, and that is sort of a gauge freedom, which I think has physical significance that I'm going to discuss a little bit further along in the talk. Okay?
But of course, just continuing Gautam's question, if you had physical probes like D-branes, then that would be complicated dynamics. Things that carry degrees of freedom.
Well, they don't carry n squared degrees of freedom, right? If they don't have horizons. So.
Sorry, but you have a physical picture of what this might be? Is it electric lines of flux or something?
Information.
Yes.
But in a gauge theory, literally the entanglement, in a sense, is almost dominated by gauge constraints or something. N squared constraints. If you take a little bit out, it's hugely entangled with the rest. Okay.
Well, I mean, that's always true that you have an area law.
But maybe because you want vector fields and
Yeah. Yeah, but I don't think, so I think that this floppiness is actually important. I wouldn't try, like if you start to impose an equation on V, an extra equation, in order to gauge fix, I mean, you might be able to do that and that might be useful in practice, but I actually think that the floppiness is somehow important to the meaning of these threads. So in terms of saying it's like an electric field and it obeys like a Maxwell equation or something like that, I'm not so comfortable with that. Okay, so since the number of threads is the entropy, I want to call them bit threads. Okay. So each thread is identified with a bit of the state of A. And one thing I want to say is that this is basically the holographic principle. So the holographic principle says, the amount of information you can pack into a region is not given by the volume, it's given by the surface area. And this is saying, well, the reason is because you're not counting point-like objects, you're counting one-dimensional objects. That's why you get an area. Okay, so this is essentially a form, some kind of precise form of the holographic principle. Okay. Now, how does it help answer the questions that I started with in terms of the original version of Ryu-Takayanagi? Okay, well, the first thing is that you can show that as A varies, regardless of what the bottleneck does, V of A changes continuously. So what happens to the threads is they're constricted. The place where they're constricted jumps, but the thread configuration itself varies continuously. Okay. Now, what about all this like mutual information stuff?
So at a phase transition point, they're constricted at two places.
Right, that happen to agree. Yeah. Now, let's consider two regions. maximize, so in general, you can maximize the flux through A or B, but not both. Okay, so this, let me just draw a picture that will make that pretty clear. So essentially, whatever the maximum flux, you can maximize the flux through A. This is my A and my B.
And then having maximized that, you choose a maximum for B.
Having maximized that, you now can't maximize B and get the same as you could have gotten if you hadn't maximized A. Okay? So they basically interfere with each other. Okay? And they interfere with each other when there's some joint bottleneck, which is smaller than the sum of their respective bottlenecks. In other words, they interfere with each other when S of AB is less than S of A plus S of B. Okay?
I have a question.
Yeah.
So the first thing where you said VA varies continuously.
Mm.
So VA is of course not one thing.
Yes.
So is it that if whatever representative you start with, you end up with a continuous path?
Yeah, so the correct statement is that V of A can be chosen to change continuously. So in other words, within the space of V's, it looks like this. I was wondering if somebody was going to ask me this question. So let's say you have some parameter like the separation or something under which there's a phase transition. And then you have the space of V of A's in some abstract sense. And let's say this is the place where there's the phase transition. You have the space of V's kind of looks, has a bit of a jump. Well, actually, a better picture, sorry, let me draw it the other way. A better picture is like this. Draw it the other way. So anything in here is an allowed V. And there's some constraint which goes off, but is no longer the strongest constraint. And here there's some constraint that goes off, but is no longer the strongest constraint. So it's always the strongest constraint that wins, of course. And what I'm saying is that you can always choose a V within this space that's perfectly continuous. Of course, you can also always choose V to jump. You could do that whether or not there's a phase transition. So
Just the space of functions V of A varies.
exactly.
But suppose you start off with a V of A on the left hand side, which is I don't know, it shows you.
Yeah, so starting from any V, at one side of the phase transition, you can follow it continuously across the phase transition, and end with some V on the other side.
But what would a choice that jumps look like?
Well, I mean, nothing stops you from just deciding to,
Even before the phase
at any point, decide to switch to a different V.
But is there a V such that you're forced to jump?
No, there's no. What I'm saying is, you can prove that you're never forced to jump.
You think of it as a pipe with two bottlenecks. You're increasing the size, you're decreasing the size of one of the two bottlenecks, something like that. The flow goes continuously.
So that's the nice thing of the flow. The flow is continuous, but where the choke is.
Yeah. And the point is, you shouldn't be too bothered by the fact that the bottleneck has jumped. Yeah, there's one could make sewage jokes. Lots of sewage jokes in this talk, but I'm trying to keep it on a certain plane Okay. Let's see. What you can prove is that you can maximize the flux simultaneously simultaneously, well, let's put it like this, through A and AB, or B and AB. Okay, that's an easy theorem to prove. Let me give an example. So, some very simple example. Let's say we have these are both 2, but they have a joint bottleneck, which doesn't allow you to simultaneously maximize through both. That would have been 4, but actually the joint bottleneck is only 3. Okay? So, what is it going to look like? Okay, this is the cartoon part of the talk. And so this I will call B of A, comma B, and this I'll call B of B, comma A. And this is related to what Shiraz was saying earlier, that essentially you can think of this as that you're going to maximize on AB, but the way you do that is to first maximize on A, and then subject to that constraint, you maximize on B. Okay? Another way to think about it is that subject to the constraint you maximize on AB, you minimize on B. Okay? So these are all useful ways to think about these.
The thing I'm slightly sorry not clear is if you just wanted to maximize in AB, would you get the correct answer by first maximizing on A and then in that set maximizing on AB?
Well, that's the little lemma that I haven't proven to you, but it's intuitive and it's not too hard to prove. Okay? I didn't prove that to you, but that's exactly the statement that I'm claiming is true. Okay? Okay, so let's do this example. Well, so let's look for V of AB. So we have 2 threads coming out of A, but now we can have at most 1 thread coming out of B. Okay. Or we can do V of BA. And here, let me just. V of BA, we have 2 threads coming out of B and 1 thread coming out of A. And the point I want to make is that the number of threads, there are threads that stay stuck to A, and there are threads that stay stuck to B, and there are threads that move back and forth. In this case, there's 1 of each in this cartoon example. And the number of threads that move back and forth is equal to the amount of freedom you have if you maximize on AB in the flow. How much freedom you still have in the flow subject to that constraint. How much flux you can move between A and B. And that is equal to the mutual information. And the number of threads that are stuck on A is the minimum number subject to the constraint that you maximize on AB. That's the conditional entropy of A. And the flux, the number of threads stuck on B is the minimum number coming out of B, given that you maximize on AB. I'm going to do equations. I know that was a lot of words. I'm going to do this in equations in a second.
So in the lower diagram, there is actually another thread coming out of A, but it's going elsewhere.
No, because I have not, this is not a configuration in which I've calculated S of A. It's not a configuration that maximizes on A.
I see.
So mutual information, just remember, is the thing that bounds the growth of correlation functions.
Sort of, yeah. It's related to that.
So the number of things that you can switch bounds the growth of correlators.
Yeah.
To what extent do you play this game with like 3 regions?
What?
To what extent do you play a similar game with 3 regions?
Oh, let's talk about 3 regions. I'm not done with 2 regions. Okay. Okay. So let me just do in equations what I just said in words. So the conditional entropy is defined in this way. integral on AB of B of AB minus integral on B of B of B. But now by that lemma, when I talk about B of AB, I can talk about B of BA. In other words, I can choose to first maximize B within the set that's maximizing AB. Similarly here, I can make this B of BA. And so this is the flux on A of B of BA. Okay, this is a very handy identity. The conditional entropy is the flux through A of B of B comma A. Okay? Now,
And so therefore we look at the second diagram to get this, and the answer is 1.
So you first maximize the flow in B and then count how much of it hits A.
exactly. And now the mutual information is S of A minus S of AB, minus HAB. And this is the difference B of BA minus integral on A, B of AB. So it's the maximum minus the minimum. So I just proved subadditivity. Subadditivity is a statement that the mutual information is non-negative. I proved it because the maximum is always at least as much as the minimum of any function on any set. Okay? This also has a nice corollary, which I'll write this here. I can write this in the following way.
That went by me a bit fast, sorry.
I also did it wrong.
Yeah, it's minus sign.
Just checking you guys are paying attention. Okay, so this, of course. Okay, now you understand. All right, it started out life as V of A, but then I decided for free to make it V of A comma B. Again, I can do that for free.
Correct.
Now, I want to write this in one more way. And my point here is that this difference in flows is finite. So the mutual information is a finite quantity of separated regions that don't share a boundary. Now, normally what we do is we introduce a regulator, compute the entropies, subtract them, and remove the regulator. You don't have to do that here. You never have to introduce a regulator if you're interested in the mutual information. You can find the flow. See, the point is that the max flow is well defined even in the absence of a regulator. It will have, of course, in the absence of a regulator, it will have infinite flux. But the notion of a max flow is well defined. It's a flow that you cannot augment. It's a flow to which you cannot add a delta V with a positive flux. So you can define the notion of a max flow, and you can define these flows in the absence of a regulator, subtract them, and do the integral. Never having introduced a regulator, you get your finite quantity. So it's nice, I think, that you can work with this quantity and always deal with finite quantities and never introduce a regulator.
So sorry, I was actually at some point going to ask you that, because normally the regulator comes in because you have this boundary going to infinity or something. And you're saying even though, so you can just formally think of the boundary at infinity and think of the flows you generated, etc.
Right, as long as you can define the notion of a max flow in the absence of a regulator, which you can. You see, you can't define a minimal surface in the absence of a regulator for the following reason. You can define a locally minimal surface. The problem is, if you have two competing minimal surfaces, you won't know which one to pick unless you introduce a regulator and get finite numbers for the two competing minimal surfaces. But a max flow you can define in the absence of a regulator because, again, it's a convex program. There's no notion of a local maximum.
And you said flow is well defined, but its flux is infinite. It's just because the flux has been computed over an infinitely big surface.
Exactly.
So that's why the flow is stupid.
Exactly. Yeah.
Like the vector field R hat, and its flux measured at infinity.
Yeah. Exactly.
I mean, I just worry that to state the problem, you need a boundary. How would you state it if the boundary is offered infinity? In the context of ADS-CFT, wouldn't you need to put a cutoff somewhere?
No. So you can. The way that the way that I first defined a max flow was by maximizing the flux. That definition is not good unless you have a regulator. So I'm going to redefine it in the following way. It's a flow that can't be augmented. A flow to which you cannot add a delta V with a positive flux through A, such that you still have a flow.
I see.
So you need to slightly redefine what you mean by a max flow.
Okay. All right, I understand.
Okay, now this example, this toy example, had a positive conditional entropy of 1. And it's also interesting to consider a negative conditional entropy, which indicates you have entanglement. So here we didn't have any entanglement. We had one unit of classical correlation. We had a mutual information of 1, and that was this thread moving back and forth. Okay? But let's suppose I make my joint bottleneck even smaller, such that I now have a negative conditional entropy. What does my picture look like now? Well, now you see that I still have 2 threads coming out of A, but I can only have 1 thread leaving AB, which means the second thread coming out of A must go to B. Okay? And similarly, if I do B, comma A, this thread will move over, and this one has to switch direction. So, my claim is that, so the lessons, so we're always working within thread configurations, maximizing on AB. First of all, a thread stuck to A represents a bit unique to A. A thread leaving AB that moves between A and B represents a classically correlated pair of bits. In other words, it's 2 bits from the point of view of A and B, but it's 1 bit from the point of view of AB. Okay? There's just 1 bit of information, and that 1 bit is located in A and in B. It's redundant. And a thread going from A to B represents an entangled pair. And my point here is that this picture, I think, matches sort of nicely the meanings here, okay?
The second one is one thread leaving AB?
the thread leaving AB, in other words, so that doesn't go, so if you look at all the threads that leave AB,
Okay.
all right, ones that their starting point can move between A and B,
Oh, I see.
the number of those is the mutual, is the classical correlation.
So your previous thing, there were, what was it, 3 threads leaving AB?
Well, yeah, exactly. In the first thing, it was 3. In the first example, it was 3
And
threads.
then one of them could move
Exactly.
from
Exactly.
AB as you did VAB or VAB.
Yeah.
Right?
Yeah. So,
So, I mean, this is really remedial, but what do you mean by classically correlated and entangled?
so
What does that
classically correlated is in this box picture that you have a bit of A and a bit of B that always agree in some coding. Entangled means that together they're in a pure state. So it's the difference between, you know, like a Bell state, this would be entangled, and just a correlated state would look like this. Mixed, this is classically correlated, this is entangled. Now, if we apply these 3 lessons to a single region, so if I take a single region, so I want to talk about those gauge freedoms. I can, of course, cut the single region up arbitrarily into A1, A2, and then apply the lessons. And so what we learn is that this freedom to move threads around on A is because there's a lot of correlation in the state of A between different spatial points. And the freedom to add extra threads, the fact you have so much room to add extra threads that go from A to A, little loops, reflects the fact that there's so much entanglement within A. Okay? So this, at least this aspect of the gauge freedom, the part of the gauge freedom that's near the boundary, I think, reflects important physical properties of the theory. Okay? Okay. My third objection was strong subadditivity proof. And let me just do this quickly. I think I'll mostly leave it as an exercise.
So, correlation functions of local operators measure how correlated the things are, not how entangled.
Right. They could be due to both. I mean, they can be due to entanglement or correlation. Yeah. The whole notion, you shouldn't, this is a bit of an aside, but you should never ask in a field theory whether 2 points are correlated or entangled. It doesn't make sense. You can only ask, given 2 regions, or given a region and its complement, whether they are entangled or classically correlated. Okay, because if you take 2 regions that are sufficiently small and you trace over the rest, you will decohere any entanglement there is, and they will just be classically correlated. So in some sense, if you're asking about a 2-point function, is this 2-point function of local operators due to correlation or entanglement? It's a meaningless question. I mean, it just depends on, I mean, in some sense, it's always due to correlation, but that correlation could be due to entanglement, so.
But this is bound on the growth of, or on the decay of correlators, which is bounded by mutual information.
So the mutual information includes both. It combines the 2. The mutual information does not distinguish between correlation and entanglement. And actually, yeah, it's very hard, actually, given a state, to distinguish between correlation and entanglement.
And this correlation and entanglement, they have precise definitions.
So, the notion of a state that is only classically correlated has a precise definition. So absence of entanglement has a precise definition. This is called separable states. Quantifying the amount of, if we decide, okay, it's not separable, how entangled is it? Is it very entangled or a little entangled? That, not only is there a definition, there's like a dozen definitions that disagree with each other and that answer different questions and so on. Okay?
But the standard definition using dilution or distillation, you think that's...
Well, that's one of many. I mean, that is the appropriate one for many purposes, but there's, entanglement of formation, there's squashed entanglement. I don't even know, I can't even name them all. And it's it's not that, you know, these are somehow disputes between different schools in quantum mechanics. I mean, these are all meaningful, useful for different purposes, and the point is that the notion does not admit a single sharp definition. I mean, it's not.
So it should be many notions.
There is no one. Yeah, there are many notions of how entangled or how much entanglement there is. I mean, this is in the context of mixed states. For pure states, it all collapses down to a single notion.
I see.
So let me just say, maybe without proving it, I'll write this formula down. It's similar to what I've been doing. And here, I hope I don't. This is the quantity we want to prove. So, oops, I switched to white. This is strong symmetry. So this is the quantity we want to prove is positive. And what you can show is that it's equal to the following thing. And essentially, the way to think about this is if you have three regions, let me put C in the middle. It's the amount of flux you can move between A and B, subject to maximizing the total on ABC and subject to maximizing the amount of flux coming out of C. And what this quantity represents, it's called the conditional mutual information. It's the amount of mutual information between A and B conditioned on the state of C. Okay, so it's the amount of correlation there is left over between A and B, assuming you know the state of C, averaged over all possible states of C. And here what I'm saying is it's the amount of flux you can move between A and B if you maximize on C. So first of all, that matches roughly the meaning of the conditional mutual information. And also, I've just proved strong subadditivity because, again, the maximum is more than the minimum.
Sorry, you haven't defined VCAB. That is.
Sorry, so this is,
defined.
so my nesting thing that you can simultaneously maximize on A and AB, this is on C, on AC, and ABC.
So
Right.
first do C, then do CA, and then do CA. Okay, now I got it. All right.
Okay? So, and the proof, yeah.
Just say, sorry, why does, so this is what turns out to be true?
This is true, this is positive, sorry.
Just from using your rules, if I thought about it, you could prove that left-hand side is
Because it's a flux on A.
Yeah. So first of all, this is a little algebra.
just some
Yeah.
algebra.
Now, I'm taking the difference between the maximum flux on A, subject to some constraints, and the minimum flux on A, subject to the same constraints.
I see, why is
The constraints are, the constraints I'm applying in both cases are that I'm maximizing on A, B, C, and C. These two constraints are in both cases.
Yes.
The first term, I'm also maximizing on this. The second term, instead, BC, which in turn minimizes on A. Actually, that second part I don't even need because the maximum is larger than anything. But this quantifies the amount. Yeah.
Without, sorry, maybe I'm dumb, but I mean, It's two different maximizations, right?
No, but here, remember, it's the flux on A, right? So think of this as the minimum flux on A, subject to these two constraints.
Okay.
So you're saying maximizing with respect to B automatically ensures that you must minimize with respect to A.
Exactly.
And so it's like maximum minus A.
You first maximize with respect to C, and then imagine then maximizing with respect to A, B, C. There's a lot of freedom in that. Within that freedom, you could put some of the lines in A or some of the lines in B. And then if you move most of them to A, you've got the first guy, most of them to B, you've got the second.
And the difference is the number you're free to move back and forth.
So, sorry. Suppose you had so this is always possible that you can minimize on 3 nested surfaces. Like, how is there a bound like only on finite or nested surfaces you can maximize? Like,
No.
if I had an uncountable many number of infinite.
Well, I don't know. Well, you can have a continuum, like a continuous one-parameter family of nested regions, and then you can find a flow which simultaneously maximizes all of them.
And there's never any global topological
Right.
structure or something.
That's right. That's right. Yeah. Yeah. And that's actually kind of a nice way to gauge fix in some sense, because if that will be more unique in some sense, within some part of the bulk that'll be unique if you do that.
And we're going to make Sandeep's bound way.
Okay.
We need to.
Okay. So the only things. So first of all, there's this generalization, or not generalization, but this other inequality. And I thought when I first was working on this that this would just be an exercise. So if this is true, or follows from RT, let me put it this way, has been proven. Version 1.0, but the new version I don't know how to prove it using flows. And actually, I mean, this is not just a technical problem because we don't understand what this is telling us about holographic states. We don't really have good words to put to it, and I feel like if we understood how to prove it using flows, that might help us in that direction.
But how can you ever have a flow, proof that you can get from areas that you can't word it up?
Well, you're not allowed to just use Maxwell min-cut
Okay.
to express it in the areas. Right, I didn't do that with this, did I? I mean, this was just purely in the language of flows.
You want to have a proof that will teach you something.
Yeah, yeah.
So,
But the original statement is provable just from quantum mechanics.
No, this statement is not a general property of quantum states, unlike Strong's additivity. This is a special property of holographic states.
I see.
It's easy to violate this.
So it's a property of holographic states, and your point is there isn't a proof you can come to?
Right, from flows. Yeah, using just flows. That's no good. So we're missing some ideas. I mean, I can, yeah. Okay, and then things I won't talk about.
Wait, this must mean that this Maxwell min-cut theorem is a tough one to prove. If that was obviously intuitive from flows, then any of these would come.
Well, I'm not sure. I mean, what is true is that I don't understand how to take a proof written in one language. I don't have a machine that kind of dualizes a proof. You know,
But if that Maxwell min-cut was some simple thing in terms of flows, then you could use that in your machine. Is it a complicated proof? Is it something I could prove?
well, it's a hard. No. So using a certain amount of machinery, it's fine. There's this thing in convex optimization called convex duality, which I can tell you about. I mean, and once you have that machine, it's very straightforward.
But it's hard to just see in your mind in terms of flows.
Which proof are you talking about? The
Maxwell min-cut.
I don't know. It's like, proofs about minimal surfaces are in the category of things that are obvious and therefore hard to prove. Proving existence of minimal surfaces is like unbelievably difficult, and the more obvious the existence is, the harder it is to prove. It's like that kind of really annoying thing.
So it's the kind of thing that Landau would have considered not worth proving.
Right. Well,
That's the statement, right? life is too short to prove theorems.
Are you saying that there is a proof which reveals something interesting? Or is it, I don't understand. I thought your max min-cut whatever principle you could show to be equivalent to Ryu-Takayanagi.
No, that's the thing that I use to show that version 1.0 and version 2.0 of Ryu-Takayanagi are equivalent.
Yes.
Right?
And then I thought you were using version 2.0.
Yeah.
And since they're equivalent, if you can prove something.
Of course.
Yeah.
No.
So yeah.
So no. I mean, of course, we know this is true for flows since the quantities, since it's true for cuts and they're equal. But I think we learned something from the proof of strong subadditivity using flows. That proof did not refer to cuts at all. And I would like to do the same here. I would like to have a proof that does not refer to the cuts.
Okay. Thank you.
Okay, and now in the interest of going to lunch, I'm not going to say anything more except I'm going to say what I'm not going to talk about. One is quantum corrections. I'm having a very moment. There are three. Oh, yes.
Those are the dynamic things. Time.
Yeah, no, that's last, yeah. Bulk reconstruction and covariant flows. Okay, so these are other things you can do with flows. Thank you.
And your point is, okay, how would you do this?
No, these are things I have something to say about.
Oh, okay.
Yeah, no, these are things that I have something to say about. Yeah.
But they all sound interesting.
Thank you.
Bulk reconstruction?
Oh, bulk reconstruction is getting the metric from the entropies.
So do you want to just give us like a 30 seconds of say quantum corrections?
Okay, so 30 seconds on quantum correction.
We're already at 120.
Here's
so classical.
yeah. So you let the threads jump. You let them jump from a point
Okay,
to
so that's the same as the mother said.
It's like ER equals EPR. Yeah. That was less than 30
Okay,
seconds.
thanks.
I'm not sure I absorbed it, but
All right. Let's go to lunch.
okay, great. Well, let's thank Matt.